Good morning, everybody. Welcome to this week's version of Water Talks here at Innovize. Hope everybody's having a good start to their year and staying safe still with everything going on. I'm joined here today by Ryan Brown, another systems engineer at Innovize. Ryan, do you want to go ahead and introduce yourself?
Yeah, so I'm like I said, like John said, a systems engineer based in the southeast. Have a pretty good stormwater modeling background, so that's kind of the bulk of what we're going to talk about today. But hey, and you, John?
Yep, thanks, Ryan. I'm the systems engineer for really the West Coast and the mountain region. So really any of the states west of the Great Lakes touching the Canadian border and then the states along the West Coast. Like Ryan said, I'm his counterpart in the Pacific Northwest. I do not have as much extensive experience as Ryan with 2D stormwater modeling, which is what we're going to be mostly focusing on today. Most of my experiences in the consulting world were from a 1D perspective. But I'm here to kind of assist Ryan. He is going to be doing most of the talking about really kind of a case study or kind of an analysis he did himself using some different solutions. So excited for Ryan's presentation today. And Ryan, if you don't mind going to the next screen. For those of you who have not joined us for Water Talks, really the idea here is get away from a typical, webinar where maybe the audience sits and listens the entire time. Really the idea here is we are going to, present for maybe 20, 30 minutes, and then we hope to get some feedback from the audience in terms of questions. So if you do have a question, feel free to throw it in the questions dialog box like is shown here on the screen. We'll kind of pick and choose as we go along, but your questions will remain anonymous. And we will try to get to as many as we can before the end of the webinar. If we don't, we will be sure to follow up after. If you're interested in future Water Talks, at the bottom of the screen there, we do have a couple more coming up. Nathan will be jumping back into ICM and talking about really the storage of different swim models and managing those swim models within ICM. And then the one on the 26th is actually a case study with AECOM. So one of our users are going to join us and talk about how they use the software to set up UDF programs for some of their municipal clients. So I think if you go to resources, I think it is on our homepage, and news and resources, then virtual events and webinars, you should be able to find the future Water Talks there if you want to sign up.
Yeah, and in particular, I'll put in a nice plug for ICM in the using swim models in the ICM database, and just really taking advantage of a lot of the features and tools that ICM has to offer in terms of validation. I know from my experience converting models between ICM and swim-based models, it can be really difficult. It's not always the most streamlined process, and by using some of the data cleanup and validation tools can be really useful. So
Yeah. Thanks, Ryan. So yeah, guys, we're going to start real quick with just a quick recap or intro for maybe for some folks on the call who are not as familiar with really the 1D versus 2D modeling, I guess, discussion. And then we'll also talk about really, I guess, what products we're talking about from an Innovize standpoint. So before Ryan jumps into that, just a quick overview. So from a 1D perspective, we're really just trying to solve those 1D equations. So those are really the conservation of mass and momentum equations that I'm sure most folks are familiar with. That's really, the basis of a 1D modeling solution is we're solving those equations in a 1D perspective. That's also true for really, point features as well, like bridges and weirs. And that kind of ties into the last point there in terms of what scenarios might be good for a 2D analysis. But bottom line is when we're doing a 1D analysis, you're going to be solving equations from a 1D perspective.
the
Go ahead,
important
Ryan.
part of that is, you're making assumptions about, especially with like cross sections doing a riverine analysis, you're assuming that everything across that line is the same in terms of depth and velocity. And as we all maybe have looked at a river or something that's flowing really heavily, it can be a little bit tilted. It can have a little bit different elevations along each one of those bends.
Sure, and that's the world. That's kind of the world I'm accustomed to, or the world I came from. I didn't do a ton of 2D analyses, and we would set up a cross section. And as I mentioned in that last bullet point, you're looking at a single water level, velocity, and flow rate for each cross section. So that's where from the 2D perspective, it can be a lot more beneficial for a complex like flooding situation or a complex urban analysis, like I mentioned there in the last bullet point. So again, with the 2D analysis, a couple things that are needed. We are using a grid or a mesh. So we're calculating that water depth really over, that entire area. So, there's a lot of different terms there. If you come from the AutoCAD world, you use the word surface. That's kind of the world I came from as well. But bottom line is, we're analyzing where that water will flow in two different directions, and really as it makes its way, across that surface. So that's the last point. It does require some type of surface, and I know Ryan's going to touch on that in terms of what data he used for this analysis. There is some options there, and I know Ryan's going to touch on maybe some of the benefits of one versus the other. Already kind of touched on some of the conditions you might use a 2D analysis for. It's always a big discussion kind of in the engineering world, but really it's for more complex conditions. So whether that's analyzing a riverine study and as it approaches a bridge, or analyzing a flat floodplain, or I mentioned maybe a dense urban condition. I would say all those are pretty good scenarios at the highest level that would be appropriate for a 2D analysis. And again, Ryan is going to talk about that as part of what he did. In terms of our products, really, we kind of point to two products at Innovyze. We have, really 4 storm sewer flood solutions with InfoSewer, InfoSwim, XP-Swim, and InfoWorks ICM. For those of you who are not familiar with all of the solutions, we're not going to focus on all of them today, but Ryan is mainly going to be focusing on ICM in terms of his analysis. But really, if you want to talk about 2D analyses at Innovyze, we're either going to be talking about ICM or XP-Swim. Both of them are very formidable solutions in their own right, with obviously some differences in between them. We've listed just a couple of the differences there. At the highest level, I would say some of the core differences are in ICM, we're using a triangular mesh, more of an unstructured mesh. And Ryan's going to touch on some of the clipping tools you can use in ICM to kind of expedite your surface building process. And then XP-Swim, we're using more of a grid pattern for our surfaces. So we're not going to focus on XP-Swim today, but there has been some new additions in the 2021.1 release towards the end of last year, including the Quadtree and SGS subgrid sampling functionality for 2D analysis. That's specifically in XP-Swim. So I don't want to discount XP-Swim, I guess is my point. It is a great 2D solution, but really the only reason we're focusing on ICM today is that's what Ryan wanted to use for his analysis in terms of this presentation. Some subtle differences there with the engine too. ICM has its own proprietary engine and also the Swim engine in it, but XP-Swim does use the 2Flow engine. If you're not familiar with that, I highly recommend you check out their website, but that is the engine that is used in XP-Swim for 2D analysis. So that's just a quick recap of our products, and if you're interested in talking more about how you might use them for a 2D model, feel free to reach out to myself or Ryan, and we can take that offline.
So we did get a quick question. Yeah, well, I just want to make sure we clear it up before we move on, but asking about why does ICM use Swim engine, and just some of what's maybe kind of going on there. So just to make it clear, ICM's always had its own simulation engine, and the biggest difference between its solution for the St. Venant equations and SWIM's method for solving the St. Venant equations is really that the ICM engine solves for volume across the entire network versus the SWIM it converges on flow. So what we've done with ICM is basically we have the ability to create two networks, one that can run a inherent ICM engine simulation or the SWIM engine in it. Both have the capability of doing a 1D sewer or stormwater network or 1D riverine analysis. Currently, we've only have 2D capability with the SWIM engine, and it looks like we're getting some
with the ICM engine
incorporations. Yeah, and now and we're working on incorporating the 2D engine into the SWIM networks for ICM2, which should be out, I think, either the second or third quarter of this year, with one of the new releases during that time.
Yeah, and Ryan, that's a good point, Ryan. I'm glad you brought that up, or I'm glad that question was asked. For those of you who aren't familiar, and this mainly applies to the States, ICM is a proprietary engine that was developed by our team in the UK. And if you go over to the UK, Australia, really anywhere outside the US, everyone is using ICM from a municipal standpoint, and of course consultants as well. But mainly our larger customers, of course, use ICM. It's a lot more robust solution for a lot of different reasons in terms of a work group solution. But the SWIM engine was not in that tool as of, when did they put that in, Ryan? That was within the last 3 or 4 years?
The SWIM engine?
Yeah.
Yeah, it was just, I think it was version 10.5.
Yeah. So really,
2020, Bob's letting us know.
Okay. Thanks, Bob. So, really in the States, people want that SWIM engine as well. We have our reasons why we love the ICM engine, but people want the SWIM engine as well. It's a standardized, kind of thing in the States. So one of our clients, actually, just a quick example, they are using ICM and they have it automated to where they're using the ICM engine and they're using scripts to run a parallel simulation in the SWIM engine. So we've been got a lot more traction here in the States recently with ICM, with the addition of the SWIM engine. So now users can use either the ICM engine on their network or they can use the SWIM engine as well. Yeah. So yeah, that was a great question. And
I know we got some more questions coming in, but I'm gonna hop ahead still, just to kind of get to the bulk of what we're hoping to cover today. So this is, like John said, kind of a case study for some flooding that occurred in Iowa City in 2008. From upstream in the catchment, major rainfall up there, and how it impacted things in Iowa City and the flooding that occurred. And you can see over on the left, that's a picture of it. During this time, I think it's Iowa State is located in Iowa City, or the University of Iowa, one of those, but they went out and collected 23 watermarks throughout the different area, and then based on as-builds and pictures and a 1D HEC-RAS model that was provided to me, along with land use and flow data and stuff like that from the event, and DEMs, I was able to build this hydraulic model and be able to calibrate it, and then come up with the results. So with what I did exactly for building these models, I built a total of 5 models, each one having variants of detail in the mesh. This detail was added primarily using the terrain sensitive meshing, and I've got the next slide that goes into a little more detail about what exactly that is, but basically is adding in detail where there's steep terrain and in more flat areas, as you can see in the picture here, where there's not a lot of detail in those flat areas. Buildings I put into the mesh based on using porous polygons with a low porosity value, to represent kind of the windows and doors and things like that. As water kind of infiltrates through some of those areas, you can see some of the buildings up here that those are in. And then the hydraulic structures, the things like the bridges throughout here were represented using 2D bridges in ICM. These simulations were run for a period of 1.5 days in the model, and they were run to steady state for a couple of reasons. One is because I didn't have the full hydrograph information available, and two, in talking with the people that supplied me with this information, it was really an appropriate approach because the peak flow that was experienced during the storm really lasted over multiple hours, 3-4 hours at least, just kind of sitting at that steady, basically being at a steady state. So it made sense to just run into steady state and be able to calibrate it from that data. So terrain sensitive meshing, if you aren't too familiar with ICM or not familiar with it at all, it's a really nice tool to be able to add in detail, like I said, to areas where there is steep terrain and not where there's areas that it doesn't matter so much in flat areas. As we were kind of talking about before, ICM uses a unstructured mesh where each one of the cell elements is a flat elevation. Versus some of the ones like Macras or like we were mentioning recently added to XP Swim, the subgrid sampling and things like that. So being able to add in detail without having to go through a lot and build in a bunch of breakpoints and break lines makes it really, really easy to build your mesh rather than having to spend a bunch of time putting in breakpoints and break lines. And in fact, I pretty limited in what I put in as far as break lines and break points. Obviously, I wanted to add them in certain areas, but for the most part relied on the terrain sensitive meshing to build these different things. It's also a kind of a shameless plug for a recently new addition is clip meshing versus the classic method. So if you've ever had trouble building a mesh and you have maybe buildings that are really close to each other or a building file that has vertices that are really close to each other, you can end up with very, very small element sizes. And that has a disadvantage because the convergence equations have trouble converging at those points because it has to do so many more computations in those areas where it's small. What clip meshing does is it actually does a pass without regard to really any kind of features that might impact the mesh, like hydraulic structures or buildings or porous polygons or anything like that. So it goes through that first pass and then it goes through a second pass where it does take into those counts and quote unquote clips out those areas and just rebuilds the mesh around that. So it does a couple of things where especially in very large models, it can be much faster at building the meshes. In some cases, I know they did some testing and I'm not sure what size of the model was, but up to 4 times faster building those meshes, and then also has the advantage that I forgot that it can be much faster, and that it's able to if you make one tweak in one area, so let's say you add some more buildings in one part of the mesh, when you go to remesh it, it's not going to totally mess up your it's not going to change the meshing that happens in another part of the model versus in that classic meshing. At least in my experience, I'll change one small vertice or something like that, and the entire mesh will change as far as the format and things like that. So
I think that's something we can all relate to, probably. So
yeah.
Ryan, we do have a couple questions, just since you're talking about meshing,
Sure.
and you're on the subject. One person asks, we have a couple questions. First one is ICM using a 2D swim mesh similar to PC Swim?
So no, and I mean, I have to claim some ignorance of not knowing PC Swim all that well. From what I do understand about it, the solution is a quasi 2D where it almost, I'm sure a lot of people out there have built fully 1D models, whereas in some situations you might want to build 2D models. So like if flooding occurs at an outlet, normally you would attach with a weir or something like that. You would attach a weir, say like if it's gonna continue down a gutter or cross a road or something like that. That's my understanding of what essentially the 2D is doing in PC Swim, when we're not doing that at all. It's a fully implicit 2D solution.
Yep.
Um,
All right, and then the second one, was just asking about if you could just elaborate. I think you elaborate a little bit further after the question, but specifically they're asking about the max height variation within the terrain sensitive meshing.
Yeah, so there's two things that I manipulated in particular, and that's the maximum height variation and also the minimum element area. So the biggest thing for the terrain sensitive meshing is the impacts of this maximum height variation. So basically, or what the program does is it goes through to try to build a mesh based on some of these initial parameters, like the maximum and minimum element information, and then if it runs into a case where that element crosses an area where, compared to the ground model that's being used, deviates more than that maximum height variation, then it's going to split that cell in half and then rerun its program to build the mesh, and then see if those two elements are now within that tolerance, and if it's not, then it's going to keep going through that routine of having those cells and then rebuilding.
All right, and there was one more question, but go on, Ryan. I think you'll address some of it with the rest of your presentation.
Yeah, so this is a little GIF that walks through just the differences in the terrain. So like I said, I built 5 models, used the terrain sensitive meshing. So we started out with that one. We go to something less detailed, even less detailed. And then I think I've got one more, but you can see how the progression, goes from something really, really detailed. And in this next slide, comparing, again, the two things that I changed were the maximum height variation, which was 3 feet in this most detailed, with a minimum element area of 10 square feet, versus one that had a maximum height variation of 20 and a minimum element area of 250 square feet. So I was hoping to accomplish two things. Is when one was to eliminate the keeping the same level of detail on a relative basis between each one of these by using the terrain sensitive meshing. So just trying to keep things more on a relative basis more than anything. So this is just a summary of what these model builds look like, and then obviously the simulation times. I mean, I know I would always struggle to try to find some good balance between a reasonable simulation time and one that keeping something that would be still give me accurate results and stuff like that based on what I was trying to accomplish. So again, I just kind of named these just to keep it kind of straight in my head, based on the maximum height variation. So we've got a 3-foot deviation, a 5-foot, 10-foot, 15 and 20 foot. As you can see, it started out with 1.5 million cells and went down to around 75,000. So as you can see, there's obviously a big progression between the simulation times, where we're looking at almost a day for the most detailed model, down to about an hour for that less detailed model. But hopefully we'll see, bring the point that in the results that this makes a big difference. So these are the results that I ended up coming up with. So you can see we basically have the range, the average of the difference compared to those high water marks. And again, the only thing that I changed was the resolution between the mesh. And I think I was just really surprised with the level of change that happened in terms of higher range between the maximum and minimum differences, the differences in the average, and then also this RS root mean squared error, which is, I'm not a statistician, but from what I understand, it's just a normalization method to be able to just normalize error across. It's basically just measuring the difference between observed values and modeled values. So that's just what I was trying to do with that. Obviously, the closer it is to zero, the better it is, and then also included the volume balance error for each one of these models. ICM just typically doesn't have much of a problem. Partly in the way that it solves the same Banach equations, but also because it does have a variable time step in terms of making adjustments to the time step as it goes through the computations to make sure that it has a stable solution. So after I saw those major differences between there, you know, I was like, well, I'm calibrating this model anyway. I calibrated the 3-foot model. You know, what difference does it make if I'm going to calibrate this model anyway? You know, why should I care? I can just tweak the Manning-Zins or different kinds of, you know, expansion, contraction with the structures and stuff like that to be able to help hone these in. I will say I only focused on the Manning-Zin to try to get things calibrated. But as you can see, we got closer with a lot of the different ones, probably one that's a little more reasonable, a little more palatable would be this 5-foot difference where we tweak those numbers. But what I ended up seeing, and I knew that I was going outside of these ranges, but you really get to the point that you're getting outside of really realistic ranges. So it just, I think, emphasizes the how important the resolution is in the calibration process, as well as some of these other parameters that you might be tweaking, like Manning-Zins. So this is kind of a summary of the different land uses and some of the textbook ranges that I found for each of these. We got dense trees. We got a pretty reasonable number for the 3-foot, and after calibration for each one of these, you can see we're getting close to the concrete. So it's just, you know, at a point I just kind of stopped trying to tweak things to get it lower, just because I was like, it's kind of futile. It's not going to matter because it's not even realistic anyway. Similar story with a lot of the others of moderate density and what we're looking at there. You know, of course, I'm not perfect with my 3-foot terrain sensitive difference, but as you can see, we're again getting close to basically the entire model was represented using a value more appropriate for concrete or asphalt or something like that. Same thing with low deviation. I didn't modify the concrete because it seemed kind of silly to try to tweak any of that because we're already really low anyway. Pretty similar story with the urban environment, and something that should be noted. The buildings were incorporated into the mesh, so we're not taking into account that. So I basically went with you know, values that were more appropriate to a concrete value. Pretty similar for high density residential, where we're just looking at like short grass and some trees and stuff like that. But for the most part, it's pretty close to concrete. But and then channel types, of course, which can be difficult. But again, getting close to values more appropriate for concrete. So just flipping through those. So that's the bulk of what I wanted to talk about and just kind of share, because it was somewhat eye-opening to me. I mean, I started out just trying to figure out, you know, just for fun to see, you know, what difference does this make? Is it really going to be important? And so then I just kind of snowballed it into this progress. And I mean, I'd love to hear feedback on, you know, suggestions for improving this type of analysis, or ideas for future kinds of case studies and stuff like that that might be interested. But I think we can hop over to questions if you're.
Yeah, and I'm just gonna work my way down, Ryan. The first one is kind of twofold, but the second part has also been asked a couple times. So the first one, people are just asking about, I think, you know, what machine and any GPU add-on that was used for the simulation, really the specs for the simulation. And then they also were wondering just a rule of thumb for meshing parameters that try to account. I'm sorry, that's my My model ranges in size from 5 to 40 square miles and sometimes runs for several days. Okay, that's just on top of that. They're asking for a rule of thumb for meshing parameters and also computer specs.
Yeah, so we definitely used GPU in this. Now that I'm looking at that, that's not right. My computer has a Nvidia P2000 GPU card in it, which I've been told is pretty decent. Not like the best in the world. The ones that can be $10,000 or something like that. It can be some of the more powerful ones like the Nvidia Tesla cards. But then from what I understand, pretty standard CPU aspect of it. But because it's all in 2D, I think we're mostly focused on the GPU card and the capabilities there.
And Ryan, for those on the call that aren't familiar, maybe it'd be good just to kind of a quick overview of the value prop for that GPU card or that that processing time, not only for ICM but for XP Swim as well, because I know they're a little different in terms of the licensing for each product.
Yeah,
touch on that a little bit for some of the newbies on here.
Yeah, because GPUs is a different add-on for XP Swim versus ICM that uses that comes with essentially the GPU capability. I think default when you create a run, it doesn't come through as GPU, but I could be wrong on that. But it's just in the settings here, and then the 2D parameters, and then basically you're checking that box if never, if suitable, and then always. They do have to be a certain type of GPU card, and I've just now lost. Needs a certain capability, but I think most of the NVIDIA cards are fine with it. Anything that I would imagine if you're running AutoCAD and stuff like that, you've probably got a decent GPU card. But that's where that is. I know that I've run plenty of models that have, like I said, I think I created a run and the default is to check the box never. And then I get frustrated why it's taking so long. And I realize that I have that parameter.
Didn't check it.
Yeah, it's not checked. So.
Real quickly. All right. Moving down the list here, which parameter is most sensitive in terms of run times?
I mean, I would definitely say detail on the mesh. I mean, I think that's pretty evident. The more elements you have in your model, the more computation that's going to go into it, and it's going to have more trouble converging on a solution, different things like that. And so that's why it becomes important too with the details. If you have those like coincident points and stuff like that, and like I was talking with the clip meshing, that it can remove a lot of that stuff and be able to remove a lot of those small elements from your model and not have to run through those computations and stuff like that.
All right, next one, question on grid convergence. Any suggestions on best practices to do that? In other words, how fine is fine enough?
That was something that I was hoping to maybe get a little deeper dive into, but I couldn't wrap my head around what exactly. But basically proposing that question of using this data set to say, hey, maybe the 5 foot difference isn't significantly different. But again, that goes more into, I think, the statistics aspect of it. Like I said, I'm not a statistician. I know some statistics, but being able to say that there's a significant difference between two different results, I'm just not totally sure how to do. I think with the fact that I was only changing one parameter kind of speaks to that, and be able to highlight that these differences we're seeing are because of the mesh. I think the good news with it is that with less detail you are increasing the the water surface elevation. So, i.e., you're creating a more conservative model. And this kind of goes into one of the questions I saw about some of the just like spatial differences to being able to see these exported flood maps. So I have the actual flood boundary here, and then I have checked on right now the 3-foot boundary. If I compare this to this 20-foot flood boundary, you can see some pretty big differences. And of course, if you're doing like a FEMA study or something like that, or in a FEMA regulated area, or if you're doing a comparison where you're looking at an existing versus proposed, it doesn't, I don't think, quite matter as much. But if you're doing a little neighborhood study or some smaller things, you could imagine that these kinds of impacts are going to have implications as far as the risk profile for the area, and it could mean that some areas aren't able to be developed because they're concerned that it's going to flood during certain events. So it's that type of thing that I think really concerns me. I think there's some other things as far as just the way that the hydraulics is differently computed for pressure versus free surface flow and stuff like that. So for instance, if you have a bridge that's modeled as being pressure when it's really free flowing, you can have some differences there and some of the issues there and some of the just tweaks between those different kinds of models can really impact the results as far as being able to compare an existing versus a proposed. And so hopefully that answers that question. Are you?
Yeah, I want to knock out a couple at a time because there's a lot in here, Ryan. But one is, why is an ICM maybe preferable over like a HEC-RAS for 2D modeling? But then someone else also asked about our product specifically, kind of going back to the first slide in terms of XP Swim versus ICM. I figured that question might come up. Their question specifically was, I'm not familiar with ICM. It's my understanding ICM is typically more of a riverine focused model with the ability to add some swim components, while XP Swim is a more robust swim model that can add some more riverine components to it. Would you agree with that? So I guess, Ryan, yeah, just if you can maybe start off, maybe differences between some of those other solutions outside of Innovyze, and maybe some of the differences between ours too.
So I think some of the big differences with HEC-RAS, and I didn't want to dive into it too much, but I did put together a 2D HEC-RAS model with the same data. I'm not going to claim to be some absolute expert on HEC-RAS 2D, but I did have a really good foundation where I came from with HDR and learning it from some of those guys over there who've worked on the alpha and beta versions of the 2D HEC-RAS. So I'd say I have a good basis. I'm not going to say I'm an expert. I could have spent more time building it, but the primary results that I got from it, I put together this hidden slide, but these same metrics, these ranges are far from the level of detail in that situation. I use the full momentum solutions, but this took almost a day and a half to run. And it has significantly fewer model elements than even the most detailed, or yes, I guess it was somewhere in between some of the detail of what I did. The other big difference really is that it doesn't have the GPU capability where you're able to use the GPU card to help speed up the convergent processes, and then also that you can only do 1D culverts in it, and that was part of the reason I didn't want to really highlight on this, because I don't feel like it's as much of an apples to apples comparison, because what I had to do was take the area under the bridge and convert that to some equivalent culvert for my 2D model in HEC-RAS, which yeah, I mean, you can imagine it's just a box. I mean, I use the width of the roadway and just divided out the area to be able, or use the area and divided out the width of the bridge to come up with the depth. But it's not nearly the same level of apples to apples comparison. And I'm sure there's different things that you could do to be able to calibrate. I definitely don't have much experience calibrating HEC-RAS models, but just something that, yeah. And then I guess the last thing, ICM uses depth averaged or average depth cells versus HEC-RAS uses a subgrid sampling method for being able to solve everything. So you might get a better inundation area with that kind of method, but it is important to note that even so, it depends on what you're looking at. If you're looking at velocities or something like that, you're still calculating one velocity across that cell face. So, you're not maybe going to get as clear of a picture there.
Yeah, and I know there's some other subtle differences. Ryan's hitting the ones I think more specific to this presentation, in terms of scenario management, a little bit more advanced stuff like hooking up radar rainfall, and maybe a live hookup to your SCADA system. It's when you start moving into a little bit more, I think, advanced setups in terms of your model. There's some benefits with ICM specifically. It's a little bit different conversation with XP Swim. So yeah, Ryan, is there anything you want to add on that last part of XP Swim versus ICM?
For XP. In my opinion, I think it comes down to a lot of workflow issues. I mean, I started off with, I guess I started off with HEC-RAS, but with my background in stormwater, it was more about using XP Swim, and then it was only later that I started to dive into ICM a little bit more. And I think that's the position that honestly, it comes down to marketing and stuff like that. So ICM and XP Swim used to be competitors a couple of years ago. The two companies merged, and so that's why we have the offering of both. And so they can do the same thing. Like I said, they calculate things in a little bit of a different way. I think XP has some advantage now that it, before you had to have all the same cell sizes, and with the quad tree, you're able to add in some more detail in certain areas and not have that detail in others. But then also the subgrid sampling, being able to, again, get a more accurate picture of your flooding area.
And we're happy to talk about more about that. I threw our emails in there. If anybody wants the recording, there's a couple questions on that. If you have more questions around anything that we discuss, including the differences with our products, of course, feel free to shoot us an email. Okay, Ryan, I'm gonna just kind of start going all the way down here. So I got a few. What data did you use to model the riverbed bottom?
Honestly, it was the DEM that I was given. I know it has the bathymetry in it, but I don't know the specific details on how exactly they obtained the river bottom. I know it's in there because you can see it in the detail of the mesh. You can see the steep banks in there, how it comes down off the bank into the actual riverbed and the bathymetry, but I'm not totally sure on how that got built.
And then I think we answered the question on the GPU card, but the same person had a question around any suggestions in parallel processing in ICM in terms of how to choose the parameters for a 2D setup.
Yeah, so we do have some metrics for that. I'm now that I'm looking through some of the questions from one of our support staff in the UK, that it's the NVIDIA GPU cards with the CUDA CUDA technology.
There you go.
So that was the thing that I was trying to remember with the NVIDIA cards. I knew there was something specific with them, so it just needs that CUDA technology within it. And and so we do have some metrics or some information as far as different GPU cards that were used on the same model to be able to kind of look for some optimization. Then from my brief understanding of where to call that cost benefit point can be hard, and it really can be an internal discussion and a business decision on how much do you want to spend on something, how much is it going to be worth it to you. That's a whole nother discussion. From what I've basically seen, the more expensive the GPU card, the better it's going to perform, plainly put.
Rules of life, right? You get what you pay for. Okay, so looks like the next one was just a comment, but they were commenting on your results that the 10-foot was close under the 5-foot, but had significant reduction in runtime. Did you have anything you want to add to that, Ryan?
Sorry, I was reading a different one. What'd you say?
It's the one looking at the results. The 10-foot was close enough to the 5-foot and had significant reduction in runtime.
Yeah, so that's where I'm saying is, to just look at the numbers, I feel like that's a little bit unfair in terms of, hey, these aren't that much different. Well, who's to say that? I don't really know. Like I couldn't tell you if that's significantly different or not. That goes into a whole, it could be like just a feeling or something like that. But I don't want to draw any conclusions about that type of thing without running it through some statistical model. So that's why I'm hesitant to say that one's fine over the other, but you are right. They are pretty close in terms of the results. Obviously there's more deviation, bigger difference in the average and stuff like that. But you do cut that time in, about a fourth there. So certainly something I'd be more interested, but I just don't have that statistical knowledge as much. I am seeing one that with from somebody out there saying that HEC-RAS will now support 2D culverts within the mesh and 2D bridge modeling. I was wondering if that's in the 6.0 release. Can you comment? Because I know there was a bunch of stuff added in the 6.0.
Yeah, that's Ryan.
And I didn't build my HEC-RAS model in 6.0 because frankly, it wasn't out yet.
And Ryan had another question too.
5.0.7. Okay.
Yeah, sorry, just to jump to that one. You mentioned only calibrating hydraulic parameters. Did you have measured runoff rates to use for calibration of flow in addition to the water surface elevation to ensure your hydrology was reasonable?
I'm trying to find that question so I get a better understanding.
The third one from the top.
Third one from the top. I'm not seeing the same one.
Phillips.
Oh. Image calibrating.
And while you're reading that, it does look like it was.
So I mean, I just used inflow hydrology. The flooding that occurred was mostly from, this is a big Midwest river where typically in these situations you have, a huge amount of rainfall in the upper parts of the catchment, and then it kind of slowly progresses its way down. So I know that's where a lot of the work that maybe the Army Corps does in terms of understanding flows that are coming down the Mississippi or something like that, how long it's going to take to peak and how long or what kind of diversion measures should they do. So it was a pretty similar situation here. Like I said, I didn't have the full hydrograph, but I did have pretty good information as far as that the peak flow in this situation did occur over multiple hours, and so it was safe to assume that it was a quote-unquote steady state point that these high water marks were taken. So that's why I did it that way. If you're not familiar with kind of that process, instead of putting a hydrograph into your inflow information, I simply just ramped the hydrograph up from 0 flow to the peak flow, which I think was about 42,000 cubic feet. So I didn't do anything as far as calibrating or changing anything in the hydrology, just because that was pretty well written out. And I didn't do any kind of like rain on or anything like that.
All right, we do have a question around the mesh clipping. Does that exclude those elements from the flow path analysis?
It could, depending on what exactly you're doing. So, hopefully I explained that pretty well. But so in a traditional meshing method, it's going to look at the hydraulic structures and different kinds of features, like maybe holes in the mesh or buildings that you might put in different ways. In ICM, we normally do that with a porous wall, and we might make that porosity 0, or we might make it 5 or 10% to represent maybe the windows or doors that flooding still goes into these houses and stuff like that, just not as quickly as what the Manning's in for the surrounding area would represent. So the clip meshing, instead of taking that into account when it first builds the mesh, it goes through a pass and doesn't consider those at all. It goes through a second time where it again, quote unquote, clips out those different pieces of the mesh, and then rebuilds the mesh around those certain elements. And so that's where I was saying, if you change one small vertice or something like that, it's not going to change everything in your mesh when you go and remesh. It's just going to change in that localized area your mesh, so it can make it easier if you have some results from a previous run. Maybe you're doing existing versus proposed, and you want to see how some proposed buildings or something like that and impact your flooding area. It can make it a little bit easier as far as making that true apples to apples comparison, since the mesh is going to be the same in those different areas.
And Ryan, the next couple are all pretty similar, so I'm going to kind of lump them together. Okay. The question was if there were really any 1D elements in this model, and then they were kind of wondering, well, they said, is there going to be a future water talk on linking 1D river and 2D flood modeling? But maybe you can talk about that a little bit too, in terms of the whole 1D versus 2D discussion. You talked on a little bit at the beginning, but might be based on these questions just to hit that again.
Yeah, so this is a fully 2D model. There were no 1D elements that I used in it. Like I said, the bridges were using 2D bridges, which from what I understand, kind of just uses a free flow for the most part. And then once it gets to a pressurized flow condition, it uses the Priestman slot method for, creating a fake free water surface so that the St. Venant equations still work. The biggest reason I did that was because it was easier. And in my experience with ICM, you don't run into as many problems with run times because it is so much faster in the routine. For a lot of people that do the have a 1D channel and then the 2D floodplain, normally that's done for speeding up the simulation. You have the bulk of your computations within the channel bed, and you use that area to be able to, and since the 1D equations are so much faster in the solution, it can make it a lot easier just to do that, since a lot of those assumptions are fair assumptions to be made. And then once you spill out into a flat or a coastal floodplain or something like that, where you're really not sure where the water's going, that's where you implement the 2D. Unless somebody else has an opinion on why you would need a 1D channel and the 2D space in the floodplain, that's my biggest understanding of being able to just speed up the simulation.
Next one, I'm facing a lot of instabilities when setting up a three-way coupled model. What are the common pitfalls, and how do I make it more stable?
So I'm not sure what a three-way coupled model is.
Yeah, if you don't mind elaborating on that, that would be great. I don't see anything more from that attendee, so we'll let that one sit for a second. Next one, could you explain how to create the initial conditions for a 2D model?
Yeah, so it's yeah, I guess we'd be mostly talking about, maybe differences between a steady and an unsteady model. In a 2D model, it's simply an unsteady analysis. So you need boundary conditions. You need an upstream and a downstream boundary condition versus a steady state model where you just need the downstream. And if you go through the standard step method that HEC-RAS does, it calculates it from the most downstream point up to the most upstream point using just the peak flow that you give it. For a 2D model, your downstream boundary condition can be very similar to what you would use in a 1D model, which could be normal depth. It could be a specific, it could be critical depth, it could be flows, it could be any number of things. And then the upstream, I would say normally, maybe you might use levels in your upstream boundary condition, but for the most part, it's some kind of flow. So you introduce flow from the upstream point and kind of let it flow down into the bottom. So if I play through one of these, you'll basically see that. And I think I have flow coming in from the upstream, but it doesn't really matter since it's a steady state. So if you use like a level on your downstream end, you run into situations where you might have flow backing up. But that was a lot quicker than I was thinking. But flow is basically introduced at this top line using a inflow parameter. So I've got it just set up for 2 days, but I've got the flow from the main river, and then there's some tributaries here. So I guess for something interesting too that I know a lot of models struggle with, but ICM, because it has it's called an initialization phase whenever you set things up. So instead of having to necessarily ramp up the hydrograph like you would in some models, you can just tell it at time 0 there's 39,900 CFS coming into the model, and it's not going to have as much of an issue with that because it reaches in its initialization phase of a point of stability before it jumps into the computations and stuff like that. Then we can look at the downstream.
Yeah, we're coming up on time. I was just going to pick out a couple more. And for all those that we don't get to, like I mentioned, Ryan and I will definitely reach out via email after the fact to make sure your question gets answered. Unfortunately, it looks like we're going to run out of time, but there was one just interested in this particular project. How much cleanup in terms of the 2D surface fabric and features was required at the front end prior to meshing?
So, like I said, not a lot. I use the terrain sensitive meshing, which speeds up a lot of that. I think I put in a couple of break lines and things like that. But I had a building file that I used to be able to put the buildings in, and then you can see this purple area back here. These are all land area definitions. So I have different land areas in there that I, again, just imported into the model and brought those in. For any gaps in the in that land area, there's always a default value. So you can specify a default value. So in case you have some gaps or something in your land use area, it can be just, it helps it so it doesn't crash.
Yeah,
it's gonna know what to do. Yeah, it's gonna know what to do even if you don't have it in the model necessarily.
So let's end on this one, Ryan. I bring it up because I know I can't remember if I did it with you, but the Riskmaster water talks we did within ICM. So related to that tool in 2D models, do the buildings and roads to identify as flooded? Sorry, the question's a little. Do you see the one I'm looking at?
Yeah, I do.
Do the buildings and roads? which
I mean, I don't think it's going to matter a whole lot what you do necessarily around the buildings if you were to use Riskmaster. All Riskmaster is doing, and you don't even have to have the buildings as being porous or anything like that, because all Riskmaster is doing is using you go through a routine where you tell the system that these buildings are the ones that I want to analyze during my Riskmaster analysis, and then it looks at the cells that are touching that element. So if we look at the porous polygons, you can see that the elements are they don't cross over into the building; they just line up against it. So that's all it's doing is Riskmaster is going to look at each one of these cells and say that the maximum cell is this elevation, and that means there's this many feet of water within this element or within this building, and then this is how much it's going to cost, or this is how much of a risk profile it's going to get. So that type of thing. Hopefully that answered that.
Yeah, I think it did.
We do have one more
not fully understand the question, but
yeah, one more question. I know we're over time, but how long did it take to build the model? Honestly, not that long. The longest part that it took was the putting in the bridges and things like that. Just that I don't think that's ever an easy task to put in these kinds of things, but that was probably the longest because having to build in like the section data. Well, the sections weren't terrible, but having to put in like the roadway profile and different things like that, that definitely took the longest amount of time.
All right. Well, Ryan, catch your breath there. No, it's been a lot of good questions here. So, like I mentioned, for those that we did not get to, we'll be sure to reach out. After the fact, might be a day or two. We do have some just company stuff going on this week to kick off the year. So Ryan and I will be sure to get to that as soon as possible. But hope that everyone can join us next week again. This is something we'll do, I think, for the rest of the year, as systems engineers here at Innovyze. So please join us every Tuesday. We're going to have a new topic, some guests. But in the meantime, hope everybody continues to stay safe and has a good rest of the week. And thank you, Ryan, for joining us.
Yep. Thanks for everyone coming.